Testing. Testing. Me. Hello? Hello? Alright. I think that's good. I think it's working. I think we're going to start. So, welcome to kind of an improvised stream here, you know? Wasn't planning on doing this, but it was such an explosion of activity around this paper that I was like, I can't not do this stream. So we're going to be looking at a paper that's kind of completely outside of my expertise. I do have a physics bachelor's degree, but that was a long time ago, so I don't know how useful it's going to be. But this paper is called First Room Temperature Ambient Pressure Superconductor. So superconductor basically means something that can conduct electricity with zero resistance. So all conductors that we use now, like copper and things like that, there's some resistance when you put electricity through them. And in fact, when you see these little resistors, right, what those actually are is basically wire just looped over and over and over and over and over again. So like if you replaced a resistor like this with just a very, very long wire, it would achieve the same effect. So superconductors have been created before, but the problem is that they're usually require very, very low temperature. So there's this Meissner effect. You've probably seen GIFs of this, but basically it's this effect when you take a little superconductor and then you levitate it on top of a magnet. And there's even Meissner effect like track. Let's see. Maybe this, but basically people put them in these little tracks and they can like float around the track. But what they don't show you is that usually most of the time when they do this, they'll dip that little magnet inside a liquid nitrogen so that it's basically super cooled, and then as soon as it heats up, it basically loses that power. And Mikhail, there's a room temperature superconductor that requires high pressure instead. Yeah, so there you go. So it's not necessarily new, but here we go. Actually, superconducting magnetic levitation on YouTube. But so far, nobody's been able to achieve this at room temperature and ambient pressure. Ambient pressure just means the pressure of one atmosphere, which is the pressure that you're kind of sitting in day to day. And this is actually the plot of Avatar 1. Avatar 1, unobtainium, is a room temperature superconductor. So, energy conduction. So this is literally some sci-fi level shit here. Ed, people understand what's going on. I don't even know the impact of this technology. The reaction seems huge. Yeah, the reaction is huge enough that I made this improvised stream. It's already named. Yeah, so first things first, I don't know what this thing is. So we're going to look up this KUKIST. I'm not familiar with the kind of schools for this type of paper. So we're going to look this up and just make sure that this isn't some PSYOP LARP. You know, like, is this a real place? So we go here. KU Graduate School of Converging Science and Technology. Got a bunch of citations. So these people do publish papers. If we actually look at all the different papers that come out of this institution, what do we got? We got luminescence, chiral sheet assembly, large memory window for van der Waal devices, DNA as steers of quantum emitters, laser-induced phase transition. So this all kind of just seems like material science crap, which I think makes sense, right? It would make sense that this type of place would be the type of place that would come up with this. Yeah. And if we actually search for Young Won Kwan, this is going to be the advisor. So these two guys are probably just students and maybe a postdoc, and this is going to be the actual guy. So let's look up this guy's name on this thing here. So if we go to Google Scholar, and in Google Scholar you can search for people, and we're going to search for this guy. User profiles, University of Seoul, fuck, there's a couple of these guys. That's not good. Maybe this guy? Seoul National University or University of Seoul? Korea University. Korea University. University of Korea, Korea National University of Education, this guy. Brain, virtual reality, cryptography, healthcare management. Huh. Okay, that's a little sketchy. We can't find him on Google Scholar. But it seems real so far. Okay, let's get into this. So I have ChatGPT, Claude, and Bard pulled up so that we can ask questions as we run into them. Abstract. For the first time in the world, we succeeded in synthesizing the room temperature superconductor. TC, I guess this probably stands for temperature conduction, is greater than or equal to 400 K. K is Kelvin. So Kelvin to Celsius, I think it's like plus 270 something or something. Kelvin to Celsius. It's minus 273 Celsius equals 0 Kelvin. So basically you just subtract 273 and you get the equivalent 127 degrees Celsius. And Kelvin and Celsius, basically the unit of measurement is the same. So in Fahrenheit, 1 Fahrenheit is not the same as 1 degree Celsius. So the measurement is different, but Kelvin and Celsius is the same. So that makes it easy to remember. Working at ambient pressure is a modified lead apatite. So I don't know what the fuck apatite is. Lead is just a metal, right? Structure, LK99. I don't know what that LK99 means. Superconductivity is proved with the critical temperature TC. Okay, so TC does not stand for temperature conduction. It stands for critical temperature. Zero resistivity, right? So the fact that it provides no resistance when you put an electrical current through it. It has a critical current, a critical magnetic field, and then the Meissner effect. So the Meissner effect is what we were looking at, where it basically floats. So I think that's kind of how they proved it, right? If you can get a little piece of this metal to float at room temperature and ambient pressure, then effectively that's the proof that you've created a superconductor. Hey J, MCG. The superconductivity originates from the minute structural distortion by a slight volume shrinkage. Minute structural distortion. So obviously metals are going to form these kind of lattices, right? So metal lattice. So the atoms inside metal lattice atoms inside of a metal form a lattice, and the type of lattice that they form is going to be dependent on different properties of the elements. And usually if you have mixes of metals, it starts to get even more complicated. So basically there's some specific property of this lead apatite structure that leads to some tiny shrinkage in volume. And I guess that's the reason why you get the superconductivity. So the shrinkage is caused by Cu2. Cu is copper, and then Pb is lead. So Pb is the lead because in Latin or Roman language, Pb, which stands for plomb or plomo, are the Spanish and French words for lead, and that's why it's Pb, even though we call it lead with an L-E-A-D. So it seems like they substitute the copper with lead in the insulating network of the Pb2 phosphate, and it generates the stress. Okay, so it sounds like basically in order to get superconductivity, you need to have some kind of stress, and normally that stress is applied via temperature and pressure, but now they're applying it by messing with the lattice by substituting copper and lead. And maybe to answer your question here, I think, Mikael, you were asking whether or not this would be easy to make. So far, it seems like it's just lead and copper, so that's huge, right? If this was some weird, like, element or some rare earth metal that would be very difficult to get, then it would suck, because ideally every single electrical circuit in the future will include this superconductor. So if there's anything that makes this difficult to manufacture, including a rare earth element, that would suck. So the fact that it seems like so far it's just copper and lead, that's pretty useful, because those are pretty common. Okay, it transfers PB1 of the cylindrical column, resulting in distortion of the cylindrical column interface. Okay, so the cylindrical column probably refers to the type of structure that this type of lead copper thing forms, and then maybe it's something like this hexagonal column over here. Maybe that's what they mean by column. Apatite with chemically bonded water is basically your teeth. Apatite is a crystal structure. Okay. Apatite. Oh, so it's like a rock. Apatite lattice. Okay, so this is what apatite looks like. Kind of cool. So here you have hydroxyapatite. And hydroxy, I guess, because it's got these OH groups, these oxygen-hydrogen groups here. Okay. Which creates superconducting quantum wells. Damn, that sounds pretty badass. What the fuck is a superconducting quantum well? Let's see if that's a new terminology or whether that's actually something that exists already. So let's ask, explain, or Eli 5, superconducting quantum wells. Let's go here, ask Claude, and then let's also ask Bard. Superconducting quantum wells. Sandbox is a space. Kids can dig and build sandcastles, but they can't leave the sandbox. Particles like electrons can move around, but only within a confined area or well. The sides of the well are formed by a material that is higher energy, and the particles cannot easily cross this energy barrier. Okay, so basically, a superconducting quantum well is a very tiny confined space where electrons are both limited in where they can move and move together without resistance. So basically, they can't get out, but within that well, they can move very easily. Is that similar to what Claude and Bard are going to say? Enhances superconducting property. Higher density interact more strongly. The middle layer is made of a superconducting material like niobium or aluminum. I don't think aluminum is a superconducting material, right? Is that just completely made up? Interesting physics competition between superconductivity and quantum confinement. Okay, and then what does Bard say? They can be used to create artificial atoms. I think this, what the fuck is an artificial atom? I don't know if that's a real, is this a hallucination here? Still under development, but potential use in a number of applications. Imagine a swimming pool with 2 layers of water with a very thin layer of oil in between. The oil would prevent the water from mixing, and the water would be confined between the 2 layers. Okay, so I think this little paragraph here makes the most sense to me. Page 7. We're going to get to page 7. We're going to read all of this. The heat capacity results indicated that the new model is suitable for explaining the superconductivity of LK99, the unique structure that allows the minute distorted structure to be maintained. In the interfaces is the most important factor that LK99 maintains and exhibits superconductivity at room temperatures and ambient pressure. Okay, so it's all about this distortion of the crystal structure here. And then I guess here's the emails for the people if you guys want to spam them and tell them that you can secure a bunch of funding for their startup. I wonder if they have a patent for this. That would suck if they patent this. Since the discovery of the first superconductor, many efforts to search for the room temperature superconductors have been carried out worldwide. Through their experimental clarity and or theoretical perspectives, recent success of developing room temperature superconductors with hydrogen sulfide and yttrium superhydride. Holy shit, dude. Yttrium? That's the most badass sounding metal I've ever seen. It's a chemical element with a symbol Y in atomic number 39. Often been classified as a rare earth element. And I think this is maybe why people are so excited about this, is that I feel like most people probably assume that a superconductor, room temperature superconductor, would have been some weird rare earth element like this, but the fact that it turns out to just be lead and copper is pretty crazy. Namasu, they do have a patent. Fuck, that sucks. Time to create a startup for superconductors that's based in like Tonga or one of these random island nations so that you can't enforce the patent. Has great attention, is expected to be strong electron phonon coupling theory with high frequency hydrogen phonon modes. What the fuck is a phonon? What is a phonon? A phonon is a quantum mechanical concept that represents the vibrations or oscillations in a solid material the way that sound waves move through a substance. Okay, so it's kind of like a photon, but the photon that is traveling through a particle. They behave in some ways like particles. They can move, interact with other particles, and carry energy. Okay. So one important thing to think about once we go into the quantum world is that there is this kind of energy, and energy is mass, mass is energy, and particles are waves, and waves are particles. So whenever you think of photon in your head, you're thinking of like this little ball that's moving, but you can also think of it like a wave. And I think what they're talking about here with this phonon is that inside these lattices, right, one way to think about how these look is that there's little balls, and then in between them there's little springs. So all these little molecules are basically vibrating. And I guess you could think of it like this giant tangle of slinkies with little balls in between them. And if you push on one end, that wave is going to propagate through the material. And that wave is a phonon. Okay. Expected to have strong phonon. However, it is difficult to apply them in daily life because of the tremendously high pressure, and more efforts are being made to overcome the high pressure problem. For the first time, we report the success in synthesizing a room temperature and ambient pressure superconductor with a chemical approach to solve the temperature and pressure problem. We named it LK99. The superconductivity is proved with critical temperature, zero resistivity, critical current, critical magnetic field, and the Meissner effect. Okay, so I guess if they can show all of those things, then they've proved it. But granted, this isn't necessarily repeatable, right? So they could have just said that they did those, and we don't know yet. So it could be the case that they just lied about all of that and they didn't actually achieve any of these things. Several data were collected and analyzed in detail to figure out the puzzle of superconductivity: X-ray diffraction, X-ray photoelectron spectroscopy, electron paramagnetic resonance spectroscopy. So these are all different types of imaging techniques. And I guess this is how they're going to figure out what the actual structure is. So that's how they know that it's the structure of the actual apatite that is leading to this property. Heat capacity and superconducting quantum interference device. SQUID. I want a squid. Henceforth, in this paper, we will report and discuss our new findings, including superconducting quantum wells associated with the superconductivity of LK99. So the stress comes with substituting PB2, so that's the whole thing. I'll just forge my own microchip. Why does the stress cause superconductivity? The stress that usually comes from colder pressures makes the superconductivity in a conventional superconductor. Okay, so here we have a bunch of different plots here, which I guess are basically these things that they need to prove in order to show you. So you have critical temperature, critical magnetic field, applied current, temperature, applied current, applied current. So this is in milliamps, which is how you measure current. That's amps. And then voltage is measured in volts, and then you have millivolts. So this is voltage versus current. And then here you have different temperatures. So this is at different Kelvin here. So 298 Kelvin all the way to 398 Kelvin. That's probably basically room temperature. This is like the 298 Kelvin to 398 Kelvin. 298K to 398K to Celsius. Yeah, so it's basically 25 degrees Celsius, so that's basically room temperature. So here's slightly different versions of room temperature. Obviously, you have slightly colder, slightly hotter. And then I guess what they're trying to show you is that the voltage goes down. I don't know exactly what they're trying to say here. Applied current, measured voltage. So when you apply a positive current versus a negative current, the voltage is 0, or like kind of hovers around 0, but why is it kind of spiky like that? Applied current, measured voltage. So these are all three of these are the same graph. And then I don't know what OE means. I imagine the voltage graph is which voltages have 0 resistivity for different temperatures. Yeah, so as you decrease the temperature here, yeah, it seems like there's kind of like this meta pattern here where you could almost look at a line that goes up like that. DC magnetization versus temperature. I don't know what this OE is. Do they define that? OE? Various external magnetic fields. Okay, so OE is the external magnetic field that they're applying. So here they're showing you this current versus voltage for different temperatures, and here this is the current versus voltage for different external magnetic fields. And I think that the Meissner effect is entirely based on external magnetic fields. It's like the external magnetic field creates a current inside the material, which then itself creates a magnetic field, which is what's causing the levitation. So is a 3000 OE external magnetic field, is that huge? Is a 3000 OE magnetic field huge? Let's see. Is that something that we can like reasonably do at home, or is that just like an absolutely outrageous? Yes, a 3000 OE magnetic field is huge. The Earth's magnetic field is typically around 0.5 OE, and 3000 OE field is 6,000 times stronger than Earth's magnetic field. Very strong. Is not an extremely large magnetic field. Earth's magnetic field is around 0.5. A small refrigerator magnet is 100, and then MRI machines have 15,000 or 30,000. Okay, so if MRIs are probably the strongest magnetic field we can create as humans, and that's 30,000 OE, so this is way less than that. So it's like 1/10 of what we can make in a MRI machine. What is this little drop right here? That's a little weird. Right, you guys seen that? FC, ZFC. Field cooling and zero field cooling. So if you're not cooling this at all, the magnetization is lower. I guess DC here probably stands for direct current, so they're applying current to it. And then FC. What is this little drop supposed to mean here? Ooh. Big industrial electromagnet. Yeah, that's probably where this is. Critical current versus critical magnetic field. Critical current versus critical temperature. Critical magnetic field versus critical current. So as the critical current goes down, the critical magnetic field goes up. And as the critical temperature goes up, the critical current goes down. Okay. So we kind of have some idea now about what these plots are, but I still don't know enough about electromagnetism to really understand what they're trying to show here. Figure 1a shows the measured voltage versus applied current at various temperatures. The measurement was performed with direct current polarity change by each 20K increment of temperature with a vacuum of 10 to the negative 3 torr. So there's two different types of current. There's direct current and alternating current. Alternating current, which is what comes out of your wall, alternates. It goes positive, negative, positive, negative, positive, negative. Direct current stays at a specific level, and that's usually what's inside your computer. Or most electronics have direct current. Polarity changed by 20K increment of temperature in a vacuum of 10 to the negative 3 torr. So they're doing this inside a vacuum. In various bulk samples, specific resistance was measured in the range of 10 to the negative 6 to 10 to the negative 9. I think this is ohms per centimeter. Current resistance, ohms. Is that the right unit? Yeah, there we go. An ohm, which is the unit of electrical resistance, is the symbol omega. So ohms per centimeter is a measure of how much resistance you have in the material. Also, a thin film. I guess this is probably small. What is the resistance of copper? Resistance of copper in ohms. The resistivity of copper is generally 1.72 times 10 to the negative 8 ohms per meter. What is that in ohms per centimeter? Per meter, and then you gotta divide by 100, or times 100. So it's gonna be 10 to the negative 6. That doesn't seem like too far off from this. This seems about the same. So I don't know. You would think it would be much closer to 0. When will we have flying hoverboards? I don't know. Maybe soon. Also, what do you guys think about the conspiracy theory that this is a piece of UFO material? That there's a UFO hearings coming out today, actually. And they have this little chunk of a superconductor. What if that little chunk of a superconductor was gifted to them by the Lockheed Martin, and it comes from a recovered alien craft. A thin film of LK99 was fabricated on a precision glass plate by thermal vapor deposition process. Okay, so this is literally how they did it. So they have a glass plate, so I'm thinking like basically a sheet of glass, and then thermal vapor deposition. So basically, kind of like the steam in your shower sticks to the glass, they do that, but they do that with like lead vapor. Thermal vapor deposition. Let's see what this looks like. All right, so here we go. This is what thermal vapor deposition is. You have a negatively charged component. You have a heated evaporant. So you're basically heating this lead copper mixture or whatever it is. Or maybe they heat the lead and then they heat the copper separately. And then it's kind of like a two-part process. But then they just basically shape it into that. Why does it have these little holes then, right? Like why, if you fabricated this with thermal vapor deposition, don't you think it would be uniform? Like why does it almost look like a meteorite and it has all these little imperfections in it? I believe the UFO stuff when they show me a dead alien or a live alien. Dead alien, you don't even know. That could be a puppet. So I feel like it has to be a live talking alien, and then they have to... We got to get someone to poke it. Shows zero resistivity of the thin film of LK99, which satisfies the zero resistivity of international standards as a new superconductor. Okay, so there's some kind of standard to what zero resistivity mean. It doesn't literally mean 0 ohms per centimeter. There's basically some threshold, it seems. It's probably 10 to the negative 9 or something like that. According to the International Electrotechnical Commission standards. So there's apparently some regulatory agency. The electric field has to be 1 microvolt per centimeter, or 0.1 microvolt per centimeter, and resistivity criterion of... Okay, so here you go. This is what a superconductor... The official definition of a superconductor, according to the International Electrotechnical Commission standards, is 10 to the negative 11 ohms per centimeter. And we figured out that copper is at 1.72 times 10 to the negative 8 ohms per centimeter. What is the resistance of something cool? Maybe like graphene is 1 to the negative 6 ohms per square. I don't know what the square means there, but highly conductive, 10 to the negative 6 kiloohms per centimeter. They keep, like, why isn't there a standard unit here? Kiloohms per centimeter, ohms per meter, ohms per centimeter. I feel like there should just be a single standard way to define that. Measured voltage ranged during the applied circuit, current increasing and decreasing. Okay, so they basically changed the current up and down and up and down and up and down. The resistivity was calculated in the order of 10 to the negative 10, 10 to the negative 11. The grain boundary is decreased. The residual resistance of the thin film decreased. As the grain boundary decreased, what is the grain boundary? What is the grain boundary of a thin film of metal? What a grain is. A grain is a small crystalline region with a solid material such as a metal. In each grain, the atoms are arranged in a specific regular pattern, the crystal structure. Each grain may have a different orientation. The boundary between these grains is called the grain boundary. These boundaries are areas where the orderly crystal structure is interrupted. Might be important in determining electrical properties and other resistance. Okay, so basically the grain boundary would be in between these little holes, or maybe it's wherever the copper and the lead. Okay, let's get back to it. The external magnetic field dependence of applied current, even up to 400 K, the DC magnetization value of 0 field cooling and field cooling with 10 magnetic field units was still relative in figure 1. This result indicates that the superconducting phase still exists under 10 OE up to 400 K. So they're saying that here, okay, so whenever the voltage is 0, I guess that means that it's superconducting, and the superconducting only applies within a specific range. Okay, I think now I understand these graphs. It's basically this flat line means whenever it's superconducting. So it makes sense that at lower temperatures, like 298 K, it's superconducting for a wider amount of current, right? You can put 100 milliamps through it at 298 K and it's still superconducting. But once you get to a higher temperature, like 398 K, the band in which it is superconducting is smaller. So I feel like that kind of explains this and this, right? Same thing. If you put a huge magnetic field on it, external magnetic field, it's only going to be superconducting for this small part here. And if you have no magnetic field, it's going to be superconducting for a wider range of currents. 300 milliamps seems pretty small, though. Is that usable? We judge that the critical temperature of LK99 is over 400 K. Moreover, since LK99 has a polycrystalline morphology, so poly just means many, so polycrystalline means many crystals, the non-uniform resistivity of the bulk sample can be examined as intergrain boundaries, intergranular vortex flow, free vortex flow. So non-uniform resistivity of the bulk sample is basically kind of what we were noticing, is that this piece of metal is just not very smooth at all. It has all kinds of little holes in it. So I guess every time there's a little imperfection, there's a grain boundary, and then that grain boundary leads to issues. Free vortex flow, polycrystalline. The Josephson-like phenomenon for the underdamped junction of a superconductor normal metal superconductor or intergrain coupled superconductor and the thermoelectric effect of the inter or intragrain were also observed. What the fuck did I just read? All right, let's take a big sip of yerba mate here. We need some more caffeine. Figure S1A. So figure S1A. That's just the figure that we already looked at. Is figure S1A? Oh, figure S1A means figure supplementary 1. So it's going to be all the way down here. So in the supplementary section, supplementary materials, normally in a machine learning paper this would be called the appendices, but here I guess they're calling it the supplementary materials. So figure S1 is the first figure of the supplementary materials, which is going to be this one, figure S1A. The deconvoluted XPF graph of lead, I don't know what these are, 4F72, 4F52, 2P1. So these are different types of lead, maybe? Here you have PB10, PO4. O is oxygen here, so this is a specific type of crystal here that has oxygen and PB, lead, and P is phosphorus. Binding energy intensities. Raw data peak sum baseline. Dude, I don't know what any of this is. Deconvoluted XPF graph. So these are the same plot. They keep changing the y-axis here. It's a little bit confusing. So it's intensities by binding energy, but the y-axis is different. You got 12,000 to 32,000. You got 20,000 to 13,000, 30,000 to 3,000 to 6,500. And this is a really complicated relationship. Like, look at all these little bumps. There seems to be specific binding energies. See the peaks to these distributions here. Holy shit. This got real. You know, it's so much material science here. Really out of my element. Did you catch that pun? I believe, Nettie, it's not metal technically, it's metal-infused stone. Is there a definition for stone versus metal? 200 milliamps is still quite good if it's the first real room temperature superconductor. I agree with you, Nobert. I don't think they're going to be using this exact LK99. I think that the reason people are excited is because this is basically the beginning of a research direction, right? There's everyone who's working in superconductors, and then probably some extra people on top of that are going to now start with LK99, and they're going to figure out a different version of it or something that has a similar kind of concept but uses maybe different elements. And the superconductor that we'll have in our electronics in 2030 probably won't be this one. So maybe it'll be able to handle more than 200 milliamps. Figure 2 shows the result of LK99 matched with Qual X 2.0 software. What the fuck is this? Qualitative phase analysis software. Free distributed. Identify crystal phases by powder diffraction data. Okay, so it's basically the software that you run whenever you're doing X-ray diffraction. So they said here, they mentioned a bunch of different imaging techniques, X-ray diffraction, XRD, and I guess this is the software that is used to plot what comes out of an X-ray diffraction machine. So we have LK99 versus apatite, 2 theta versus intensity. I guess these spikes, generally in X-ray diffraction, there's like specific spikes for specific angles or something like that. Basically, you're shooting X-rays into a lattice, and then the way that those X-rays are going to bounce and then return, it's going to tell you the angles and the kind of connectivity within that lattice, something like that. Why is this circled? It's only K alpha 2 stripped without any other processing. Uses crystallography open database to perform the search match operation. It shows that LK99 is polycrystalline. Okay, so there's some kind of open database of results from X-ray diffraction, and then they searched through this entire database to find a match. And that match is what is telling them that LK99 is polycrystalline. So the main peaks are well matched with the lead apatite structure, and a few Cu2s impurities are also shown. Okay, so the copper is actually a form of impurity. The crystal system of the original lead apatite is hexagonal with the cell parameters 9.86. I think this stands for atomic units. Atomic units. A with a dot on top of it? No? A with circle on it, material science. What is the A? Angstrom, that's what it is. 1 angstrom is equivalent to 10 to the negative 10 meters, so extremely tiny, 0.1 nanometers. So it's a hexagonal, so it's a hexagon, and the size of the hexagon is basically 1 nanometer, because 9.8 angstroms is basically 10 angstroms, and if 1 angstrom is 0.1 nanometers, then 10 angstroms is 1 nanometer. So basically 1 nanometer hexagon. However, LK99 shows a slight shrinkage compared to the lead apatite with parameters 9 angstrom and 7.48. Okay, so they're saying that you have a shrinkage here. You see the hexagon has gotten a little bit smaller. The 9.86 has become 9.84, and then 7.43 has become 7.42. The volumetric reduction is 0.48. Okay, so the parameters that define this hexagon have gotten smaller, which means that the overall volume of this hexagon is also smaller by a absolutely tiny amount. 0.48% is a very small percentage. Humankind, I love any paper that uses humankind like that, has long learned of the properties of matter stem from its structure. Okay. However, so far, the correlation between superconductivity and the structural change of material has hardly been properly clarified. In fact, the 2 main factors affecting the generation of superconductivity of superconductors discovered so far are temperature and pressure. So it seems like basically, even though we understood that it's the structure of the material that led to superconductivity, the only way we were trying to get to it was by changing the temperature and the pressure. It seems that the stress generated by the decrease in volume under the low temperature or high pressure causes a minute strain or distortion. All right, so it's all based on this idea of stress on this lattice, and if you can replicate that stress without having to fuck with the temperature and the pressure, that's how you get this. Although it's difficult to observe minute structural changes, this structural change seems to bring the superconductivity of it. Representative examples showing that the superconductivity due to external factors. Netty. Stone is metal bonded to non-metals. Okay. So a metal with impurities is stone. Pressure and the internal factors, oxygen doping. You can oxygen dope. I guess if you have a copper with oxygen, this is called oxygen doping. The structure of copper O changes from, is this copper monoxide? Is that the right way to say that? Changes from the tetragonal structure. What is a tetragon? Tetragon. That's a tetragon. It's basically 4 sides. But you have a square, parallelogram, rectangle, so I get tetragon is just a more vague, higher level version of a 4-cornered thing. To the orthogonal structure depending on the oxygen doping contents. A higher TC, critical temperature, is observed under high pressure condition. In CuO-based superconductors, it may be thought that the stress is generated by the inconsistency of the amount of change in the C-axis and A and B axis. So I think when you're defining a crystal lattice C and B and A axes, there's different axes. Yeah. So everyone's familiar with X, Y, and Z axes, and on the X, Y, and Z axes are orthogonal to each other. But I think whenever they're describing these crystal structures, they have these axes as well, but the axes aren't necessarily orthogonal to each other, which you can see here, right? The A and B axes are 120 degrees in between, and then the A and C are orthogonal, but I think that's what they mean here, is that basically they don't need to be orthogonal. affects the intermediate CuO, causing structural distortion and superconductivity because the changes in the C-axis seem to be the most sensitive to the changes in the temperature and pressure. Okay, so A and B are orthogonal to C. I don't know if this holds for all hexagonal crystal structures, but let's just pretend that it is. So basically you have sheets like this, and it seems like the C-axis is what's changing when you change the temperature and the pressure. Is you're basically fucking with that C-axis there. All other examples that we think of as appearance of superconductivity is caused by distortion or strain caused by fine physical stress. When the FeSe, this is iron and selenium. Selenium, is that correct? Selenium is Se, and then iron is Fe. Yeah, so that's selenium plus iron. Monolayer, so a single layer of ferrous selenium. Maybe one of you chemistry people can tell me what that is. On top of the insulator is stacked. The highest critical temperature is 65 Kelvin, which is actually very low. So 65 Kelvin, 0 Kelvin is basically absolute zero. So 65 Kelvin is extremely low temperature, even up to 109 Kelvin. However, the critical temperature to 10 K as layer stacks increases. Okay, so this makes sense. So if you have a very thin sheet of this Fe metal, you can get superconductivity at a slightly higher temperature. But as soon as you have more and more layers of this metal, then your critical temperature is going to get lower and lower, which is consistent, right? It would make sense that if you have a very thick piece of metal, the critical temperature is going to be very close to absolute zero, which is why this superconductivity has been such a hard problem to solve. In the case of CuO monolayer films, okay, so these are, I guess, different attempts that people have made. FeSe monolayers and then CuO monolayers. So you got bismuth. I don't know what Sr is. Cu is copper, and then O is oxygen. What the fuck is 8 plus delta? You can have a delta, you can have a different number of oxygens on this. Identified two distinct and spatially separated gap, U-like gaps and V-like gaps. Prove the effect of 3D strain from the TC in the cuprate system. BAFE SAS2 system also showed strain-induced superconductivity. So strain is whenever you take a metal and you basically like pulling it, right? Pulling it, maybe shearing it. So it seems like people have been making superconductors by applying strain to the metals, right? So it seems like these FeSe and CuO are based on temperature, and then you have a different type of superconductors that people have been working on that are based on strain, and these are the weird BAFES FeAS2. Is it real or fake? First name, last name. So far it looks real. Obviously, I don't know enough to like check this crap. Like, anybody on Twitter who's telling you that they're reading this and they're understanding this is lying to you. Like, I think the amount of material science knowledge you need to have to like understand like this sentence here, the underdamped junction of superconductor, normal metal superconductor, or intergrain coupled thermoelectric effect of intergrain network. Like, your average crypto bro or AI bro is not going to understand this paper, so don't let them lie to you. Okay, back to this. The thinner layer, the greater the stress-inducing effect, the greater the strain, which seems to be the higher the superconducting transition temperature. Therefore, we argue that stress caused by temperature and pressure brings a minute structural distortion which create the electronic state for superconductivity. Okay, so basically people have been twisting metal, straining it, and they've been lowering the temperature in order to get superconductivity. So what do we got here? We got a figure, A, B, C, D, and E. A, the top view of a C-axis of lead apatite. So we've learned that the C-axis is kind of like the vertical axis, right? So it's like the layers is C, and then A and B is kind of like the XY axis, but A and B do not have to be orthogonal. So basically the only thing that is orthogonal here is A, B, and then C. So the top view of a C-axis, this is what a monolayer, I'm going to kind of borrow some of the terminology. It seems like that the way that they describe these are monolayers. So this is a monolayer of the lead apatite. So we're looking at it from the top. And actually, here you go. Here's the axes. A is red, B is green, and then C, which is pointing towards us, is blue. So here's the actual axes for this structure. And it looks like you have PB1 and then PB2. So 2 different types of lead, maybe? This actually looks pretty complicated. It does look like it repeats. So here you have 1, 2, 3, 4. You have basically 6 here, but then you have this kind of weird, complicated structure. B, the synthesized LK99. So this is the actual little piece that they made. And this is, I think if you look in the Superconductor, okay, I'm not going to find it, but like on Twitter, on some of the releases of this, they show basically the Meissner effect with a little piece of metal floating on a magnet. I think this is the little piece of metal that they created, and they created it with vapor deposition, which is what we saw up here. But this seems a little sketchy to me because they're describing this vapor deposition process, and it seems like from everything that they've described here, it's extremely sensitive to the number of layers, right? Like it seems like from previous work, going from just one layer to more layers, right? As layer stack increases, it becomes harder and harder to get this thing to be superconducting. So the fact that this just looks so porous, right? There's like so many imperfections and holes in it. Like there's something sketchy about that to me, right? Like I would expect this to almost look like aluminum foil, you know, or like it would just be one super thin sheet that is like perfectly shiny and reflective. So the fact that this looks like a stone that you just found on the ground is a little sketchy. Is this a new paper? Recently the news has been popping up. I'm not very well informed. Could you please elaborate how this discovery will revolutionize the world? So we're going to do that with AI. Because at this point, I am more AI than I am human. So let's ask it. What are 5 things we could do with a room temperature superconductor that would change the world? All right, so we're going to give that to ChatGPT. We're going to give that to Claude. Control K. Claude is Anthropic's AI, and then Bard is Google's AI. Let's refresh. Let's get a new one here. Energy storage. Primary challenge with renewable energies is that they don't produce a consistent level of energy. Storing and transmitting. With room temperature superconductors, we could conduct storage devices that don't lose energy or resistance. Okay, so here's the thing. If you have a superconductor, you can basically just put the electricity in there and it just sits there and it just infinitely goes around, right? If you try to do that now with copper, eventually the copper and the friction inside that copper would get rid of all that electricity that you've put in there. So basically you can create infinite batteries. Pretty good. Magnetic levitation. Superconductors can enable magnetic levitation due to the Meissner effect, which allows them to repel magnetic fields. So magnetic levitating cars, that could be pretty badass. Advanced medical devices could enhance MRI scanners. You could use superconducting magnets to generate large magnetic fields. Room temperature would make these machines cheaper, smaller, and more energy efficient. Okay, so you could have basically MRIs that you can hold in your hand and that maybe would be way cheaper, especially if this is just made with copper and lead. Quantum computers, however, qubits are often based on superconducting circuits which need to be cooled. Yeah, so this is actually super cool, is that, pun intended there, whenever you actually look up a quantum computer, and I think this is the D-Wave quantum computer that Google has, this one here, the majority of this crap here is actually a cooling system. So the actual supercomputer itself is literally just this tiny little chip there. So you see that? Let's open image, new tab. The entire the quantum computer is just that little chip right there. That's it. All this other crap here is to cool it down, because you need to basically have it be extremely cold in order for it to work. But if we have superconductors at room temperature, then we could have a room temperature quantum computer. And quantum computers, like, that's a whole other rabbit hole, right? As soon as you have quantum computers, like, so many things become possible. You can basically simulate chemistry, you can simulate interactions a lot better, which means that medicine is going to explode. It's also, there's probably ways of training machine learning models with quantum computers that are infinitely faster than the ways that we do it now, right? You could basically find the perfect model rather than train it, which is what we do now. Like, the way that we train machine learning models right now, we basically feed a bunch of data and it kind of it does this gradient descent process, right? So you're changing the little weights, you're kind of moving this little marble through this hilly landscape. But if you had quantum computers, you could just instantly get to the answer, which would be fucking crazy. And then I guess you could improve the Large Hadron Collider. All right, so that's what ChatGPT thinks. What does Claude think? Magnetic levitation, faster computer, lossless power transmission, MRI scanners, and energy storage. So we're kind of seeing a repeat of the same things, right? We're seeing energy storage, batteries, levitation, and quantum computers. Is that what Bard says as well? Efficient and sustainable power grids, faster and more powerful computers, apparently powerful magnets. I don't know why that's super important, but levitation, medical imaging. Okay, so all of these are consistent amongst all the different AIs. But to me, out of all of those, I feel like the quantum computer would be the most transformative. If this is real and scalable, this is huge. Yeah, it would be huge. I'm hoping to see reproduction of this material in the near future. Yeah, I just really hope that they don't make this a patent war. You know, like, I really hope that everybody can make this, right? Because if this becomes a situation where, like, there's one company that holds the patent and then basically they slow down the entire field, like, that's going to absolutely suck. So I don't know. I feel like with these big groundbreaking discoveries like this, it should be illegal to put patents on them. Okay, lead apatite, synthesized quartz cube, synthesized Cu copper cube. What does this see? The calculated electron density map of PV1 of cylindrical column interface of lead apatite. So what is an electron density map? So this is kind of cool. This is something I do remember from physics. So electrons, the way that you were taught electrons in high school is that they're these little balls, right, that kind of like orbit around the nucleus of the atom, kind of like a planet around, or a planet around a star. But that's not actually at all what's happening. Electrons are so tiny that they're almost more like a wave than they are like a particle. You know, you think of them more like a wave of potential things. So basically, whenever you see an electron density map like this, what that's telling you is that it's basically a probability density for where the electron is. The electron is in all these places at the same time, but there's a probability that it's, so like, for example, here. Let me see if I can find this. Electron density orbitals. This is what I was really looking for, yeah. So if there's one electron around a nucleus, it has equal probability of being found anywhere in this sphere around the nucleus. If there's two electrons on around a nucleus, then they basically fall into, if you were to measure where they are, they would basically be in one of these two areas here, right? So that's kind of what they're showing here, right? Is that here is all the different places that the electron could be, right? So if you measured it, it would be more likely in this area that's white, less likely in this area that's orange, less likely in the area that's purple, and so on. And the fact that they form these weird patterns is kind of crazy to think about. But okay, back to this. This is the electron density map of the structure. And I guess what we're seeing here is the density is this curve here. So this is basically, you could think of it like the probability distribution of the position of the electron. So the electron is more likely to be here than it is to be here. Right? And I guess what they're showing here is that the green shows that it doesn't line up. Is that kind of what's going on? Is that because of the position of these... I don't know what triangle up or triangle down means. It basically means that I don't know. Maybe one of you guys can tell me. Huh. Damn. Of cylindrical column interfaces, an LK99 synthesized with different tubes. A CU and Corp tube. So you can synthesize it with different tubes. Top view of a stressed interface of cylindrical column produced by Vesta software. So this is, I guess, the cylindrical column. And you can actually see the axes here. You have B, A, and C. So this is the top-down view, B, A, and C. And then this is the actual side view. So I guess one column would basically be one thing like this. And actually we can see here, you see this PB1, PB2 here. I think that corresponds to these holes here, or these little circles here. So this is basically the top-down view. And the electron density, which is the probability of finding the electron at any single point, right? Kind of like basically a probability density, changes whether you have this copper tube or the quartz tube. Here you're substituting copper 2 with 4 lead. 1, 2, 3. There's 5 lead atoms here, though. But you see here, they're basically saying volume shrinkage. So if you put this 1 copper in there, it shrinks that tube. And when you shrink that tube, it kind of changes the electron density. And that does what? PB2, PB1, phosphate. Channel oxygen, 1/4 occupied. The side view of the cylindrical column and the predicted superconducting quantum well. EPR signals from blah, blah, blah. EPR signal of LK99 after voltage current measurement. So these are these two ones here. So magnetic field as a result, as a function, or intensities as a function of magnetic field at various different temperatures. So it seems like it's actually quite robust to different temperatures. All of these temperatures kind of exhibit the same properties here. And then in terms of magnetic field, we learned that 15,000 or 20,000 OEs is basically an MRI. And then the Earth is around 6,000 OEs. Is that what we read? Something like that. I think that UFO hearing starts soon. It starts at 10 a.m., so I'm definitely going to end the stream before the UFO hearing starts. The LK99 name was a registered trademark. Oh no. LK99 is a gray-black color. It is a superconductor with the same color as typical superconductors. What the fuck is this sentence? The lead system of lead apatite is an ivory-colored powder and an insulator. LK99 has a three-dimensional network structure shown in Figure 3A and a cylindrical column surrounded by insulating tetrahedral phosphate oxygen network structure. Cylindrical columns are arranged at intervals of 6.5 angstroms, so about half a nanometer. What is width of human hair in nanometers? Okay, so it's really, really tiny. A human hair is 80,000 nanometers. And an angstrom is 10 angstroms is 1 nanometer. So we're talking about absolutely tiny things here. Composed of asymmetric polyhedral 6 PB1ON components consisting of 2 oppositely shaped triangles as shown in the side view. So these are the phosphates with the oxygens here, these little triangles here, these tetrahedrons. Then you have the lead, 2 different types of lead, PB2 and PB1. And then right in the middle is that quantum superconducting quantum energy well, superconducting quantum well. Right there. That's where it is. The polyhedral 4PB2 are components of an insulating PO4 network structures. The modified lead apatite is expected to be PB10X, CUX, PO4, 6 PO4s, and a little extra oxygen in there just for good measure. Which one of the 4 PB2 ions approximately has been replaced by Cu2 ions at the polyhedral sites of lead apatite? One of the 4 PB2 has been replaced by Cu2 ions, which I think is what they were showing here. So these blues are lead, and then one of them is getting substituted with the copper. So that's where the copper is coming in. It's basically, if all of this was just lead, it wouldn't be superconducting. But then if you get rid of one of the lead and you put in a piece of copper there, or one of these copper atoms, then now it suddenly becomes superconducting because it distorts the whole thing. Interesting. The ratio of copper was determined based on the percent atomic data of XPS and confirmed by the Debye heat capacity model with heat capacity result and chemical formula. Well consistent with previous published research results. So how did they actually replace the lead with the copper? Resulted in a volume reduction. So the volume reduction is because copper ions are smaller than lead ions. Does that make sense? Periodic table, is copper smaller than lead? So PB is lead. It's right here. It's number 82. And then copper, Cu, is up here. It's 29. So it's actually way smaller. That is correct. Yeah, so if you have some crystal structure that is made with lead ions, which are these big fat 82 atomic weight 207.20 compared to copper, which has basically 1/4 of that, and it's way smaller. Stress was incurred in the network portion and then affected the appearance of the superconductivity. As a result of more precise analysis of XRD and XPS, it reveals where the stress from volume reduction was finally affected. For the purpose of determining the variation of PB1 positions, one-dimensional electron density calculation along one crystallography axis via Fourier transform of the calculated structure factor was used. So one-dimensional electron density, I think that's what this is. Right? So this is a one-dimensional curve, which is showing you the density across this axis here, this vertical axis. So here you have low electron density and then high electron density. Low electron density, high electron density, low electron density, high electron density. The electron density calculated along the z direction, PC, based on the 00L reflection intensities of XRD data. I don't know what any of that means. Okay, we got some equations. This is good. We have a sum. The sum is from L equals negative infinity to infinity. So this is probably an 2 pi LZ. L, F, C, and Z are the order of the Lth diffraction peak. So the diffraction peak is the peak of the diffraction plot here. So these are all diffraction peaks, I'm pretty sure. So each of these is going to be a peak. they don't really tell us what any of these variables are, to be honest. One over C, so they're normalizing by whatever the C is. See that? Z over C. You could pull out a C from all of this. The atomic coordinate along the C-axis, since LK99 has a hexagonal structure, the above equation was applied for the electron density calculation of PB1 along the C direction, C-axis. Okay, so this is what one of the few things that I've kind of learned is that you have this A-axis, B-axis, and C, which is coming up, right? Here it's pointing up. So C, they're renaming it to the Z-axis, which is a little bit confusing. I feel like they should have just kept it C-axis, A-axis, B-axis. So you have density calculation. Your electron density is 3D, right? You have a density value for every single point in this 3D volume, but you can calculate the electron density in different axes. So here they have P in the C-axis, the density in the C-axis, and then P in the A-axis, the density in the A-axis, which you can plot it. I don't know what these 00L, H00 reflection intensities are, but I think that's what they talk about here with this peak. So as a result, the position of PB1 constituting the cylindrical column is slightly shifted in the A-axis plane from the original position by the substitution of Cu2+ inward or outward. The cylindrical column is slightly shifted in the A-axis plane. So the A-axis here, which is this red axis, is what's being slightly shifted by the addition of this Cu atom. So putting just that one Cu atom in there, most of them are still these lead atoms, is going to shift just ever so slightly that column in this structure. Okay. In the repeated triangular structure of PB1 in the cylindrical column, the distance between the PB1 and one layer is increased to 2 angstroms, and the next layer is increased to 5 angstroms from the original distance of 3 angstroms. The distance through the C-axis between the layers remains almost unchanged. Okay, so in terms of the actual C-axis, which is the vertical axis, which is the kind of layers on top of each other, they're saying that that distance actually is basically the same. The binding energies of PB2 and phosphorus also unchanged. The tetrahedral phosphorus atomic radius does not correlate with atomic number like you'd expect. Interesting. So you're saying that so the number here is the number of protons, right, and neutrons. So the size of the nucleus is going to definitely increase with the atomic number, but the number of electrons that are basically chilling on the outside are going to change, right? Or going to differ. So I agree with you that the gases, right? So like here, it basically means that there's a perfect amount of electrons, so it's going to be a tighter, smaller atom, and then the things here, even though they have a smaller atomic number, they're, I guess, going to be wider because the electrons don't all fit nicely into the orbitals. I don't know a ton about chemistry, to be honest. I'm just kind of like riffing here. But I feel like it would make sense that these two are far enough away, copper and lead, that it's going to be pretty different, right? Copper has to be smaller than lead. Not only does it have a much smaller number, but it's also more to the left, which means it has less electrons. I don't know, Theo. Help us out, Theo. Although the tetrahedral phosphorus splitting value very slightly increased, so I guess this is the amount of energy required to split this phosphorus out, and all oxygen's Be binding energy are quite a bit increased by 0.21, 33, 56, and 89. And then the binding energy value of PB1 is slightly decreased. From the results described above, it can be seen that the volume reduction was caused by the replacement of the Cu2 ions, and the stress was caused by the volume reduction caused the position changes of the PB1 and the binding energy change between oxygen atoms adjacent to PB1. Okay, so basically everything that they're describing here is that this replacement of one of the PB ions with this Cu ion basically just kind of fucked this entire structure. The binding energies are now all different, and the positions are slightly different. Shows the EPR signal. It is the same as the heterojunction quantum well, such that silicon and then silicon germanium, is that the right? Si and then SiGe. Si is silicon and then Ge is germanium. Am I correct in that? Where's Ge? Can somebody find it first? Yeah, silicon, germanium, which are right on top of each other. It's kind of cool. Natural DNA in a dry state. What? DNA has a quantum well. That's fucking weird. What the hell? The EPR signal was interpreted as a cyclotron resonance signal with a two-dimensional electron gas of quantum well. What? Cyclotron resonance signal. Cyclotron resonance signal. Ion cyclotron resonance is a phenomenon related to the movement of ions in a magnetic field. It is used for accelerating ions in a cyclotron and for measuring the masses of ionized analyte in mass spectroscopy. Spectrometry. What the fuck? An ion in a static uniform magnetic field will move in a circle due to the Lorentz force. The angular frequency of this motion is based on the magnetic field. That makes sense. So I guess they measure how much these molecules move in a cyclotron. How do they get access to a cyclotron? Is there cyclotron? Is there like cyclotrons that you can just put on your desk? I guess this is a 60-inch cyclotron. Magnet cyclotron. Yeah, so I guess you could probably make a small cyclotron. I thought these things had to be huge, but it kind of seems like you can make little tiny cyclotrons, so all right. In addition, the substituted Cu2 plus ions appeared at 3000 OE in EPR signals as shown in figure 3. You should be able to find a periodic table with atomic radius values for each element. Cu is 138 and PB has 147. Pretty close. Huh, that's pretty cool. Thanks for that, Theo. So actually the difference between the Cu and the PB is actually very minute. The superconductivity of this weird thing here and then DNA. The fact that DNA is getting brought in here is kind of a weird comparison. The superconductor having interface structure like a heterojunction such as, damn dude, like look at these complicated metals here, has been shown the superconductivity. This is a typo. Has been shown to have superconductivity. Hence it is confirmed that the superconducting quantum well has generated between PB1 and oxygens of the phosphate by structural distortion and strain. Okay, so this is this complicated paragraph here where they describe this cyclotron. The whole point of that was basically to pinpoint where this superconducting quantum well was. The predicted superconducting quantum well illustrated in figure 3e. Figure 3e. So here's where they're telling you. They're telling you the superconducting quantum well is happening right here in this little triangle. There you go. Deep related to SQW, Koji et al. Already reported the similar EPR signals and found that the superconductivity with this thing, which is way more complicated. However, they did not interpret the EPR signals as superconducting quantum well and to associate it with the appearance of superconductivity. Calculated Debye temperature from heat capacity data, heat capacity curves from LK99. The heat capacity of LK99 was measured from 5 Kelvin to 400 Kelvin. I think heat capacity is basically related to resistivity. Let's ask. What is the relationship between heat capacity and electrical resistivity? That's not even the right spelling, I'm pretty sure. Isn't direct as they measure different physical properties. They can both change with temperature. This is the amount of heat required to raise the temperature by a certain amount. For most materials, heat capacity tends to increase. The exact relationship depends on the type of material. Okay, so you can't use heat capacity as a proxy for resistivity. You got joules per mole of K. And then you got K here, K Kelvin temperature. I guess we need to figure out what Debye temperature is. What is Debye temperature? The Debye temperature is a concept in solid state physics and material science named after this Dutch guy. It is the theoretical temperature that is derived from vibrations in the atoms, also known as phonons, which we actually learned about earlier in this stream. Scale for the phonon energies in a material is the temperature above which all possible vibrational modes or quantum harmonic oscillators are excited in a material and contribute to its heat capacity. Below the Debye temperature, the heat capacity of a crystal lattice starts to decrease as some of the vibrational modes fall out of thermal equilibrium. The Debye temperature thus gives an approximation of the temperature below which the specific heat capacity of a solid decreases from its classical high temperature limit towards zero. Okay, so the Debye temperature is a specific point. It's like a transition temperature. But the Debye temperature is related to temperature? Heat capacity. I don't exactly know what they're trying to show me here. This is the Debye heat capacity equation. Holy shit. What a mouthful here. You got CV is the heat capacity. R is the number of atoms per molecule. N is the number of molecules. And K is the Boltzmann constant. So you're integrating over dx, so this integral is dx here, is the what's going from 0 to theta over t. x4 e to the x dx over ex minus 1 squared. And then they pulled out basically all the constants here. So they pulled out all this crap from the integral, so this integral, really it's only the terms here that are dependent on x. Creative builds, how's the paper so far? Very complicated. I definitely have no idea what's going on. There's a lot of material science and chemistry here. It looks like they're possibly using the change in heat capacity as a measurement of phase change, possibly to determine the TC, where the material stops being superconductive. Okay, so that's kind of interesting. They're using the heat capacity as a way, it seems like you can basically measure the heat capacity with whatever this is, the Dynacool 9. Let's actually see what that is. Dynacool 9. Here we go. You're not a real scientist unless you have a quantum PPMS Dynacool. That's like the coolest name I've ever heard. Oh, look at all these different. You want to measure DC resistance? Here you go, dude. The Dynacool got you. You can thermal measure. You can measure heat capacity with the Dynacool. So I guess you just kind of put the little thing right there, and then you can measure the heat capacity. They have a dilometer. Subtle changes in a sample's lattice expansion and contraction are readily characterized using the diameter option. That kind of sounds exactly like what they want to know, right? It's like their entire paper here is based on the fact that the lattice structure is changing because they're replacing one of these PBs with one of these coppers, right? So if this machine here, this quantum dynacool, has a little attachment that allows you to detect subtle changes in the lattice expansion and contraction, that's exactly what you want. Looks like basically this tool has like a bunch of extra crap that you can buy. It has a bunch of DLC. It has like everything. Look at this. You can fucking get all these different attachments to it. What paper is this? This is a room temperature ambient pressure superconductor paper that kind of exploded overnight, because if it's true and if it's real, we're definitely going to see a lot of very cool tech in the next 10 years. TC cannot be calculated with the electron phonon. The blue line curve is calculated heat capacity of the typical apatite because the Debye temperature of the typical apatite is 280 K. The red line is the calculated heat capacity based on Debye temperature at a low temperature of LK99. So red is just... blue is the normal Debye temperature, and then this gray one is the apatite, or the LK99. So it's kind of, I guess what they're trying to show you here is that the red and the blue kind of both have this property where the heat capacity kind of stays high, but this gray one here, which is the LK99, which is the superconductor, it doesn't do that. You would think that it would keep going up, but it does not. It actually kind of starts going down at some point. I might need the glue sniffer translation of this paper. Yeah, me too. It is relatively explained by electron phonon model. In the electron phonon model, one of the most influential parameters is the Debye temperature. The heat capacity curve does not follow the Debye models, since normal vibrational mode is limited by Cu2 plus ions replacement. This result also confirms that LK99 has a structure distorted by the substitution of Cu2 plus ions. In terms of the EPR experimental results shown in LK99, the expression of superconductivity can be explained by the formation of SQWs, the superconducting quantum wells. There is also a paper explaining superconductivity with the quantum well model. However, they did not show EPR signals like ours. The EPR signal measured on the sample compared to a signal in which no current is applied, the overall signal intensities decreased, and the signal intensity of cyclotron resonance was relatively decreased. Is this the cyclotron? Does this thing also have a cyclotron in it? Features. Fully automated operation. Built-in cryo pump for high vacuum activations. I want to see like the commercial for this. Videos. Here we go. Welcome. Do you have superconductors that you want to measure? Well, now. So it's like roughly the size of like a fridge. Put the shit in. There you go. Put your little sample, insert it deep into the machine. And then you sit there on the computer and you look at it. All right. Here we go. Good to know. Look at that. You got your big rod. You're putting that shit deep in there. All right. Large absorption appeared at a very low temperature and a small external magnetic field. We also observed with YBCO and BI2212, I think these are probably other superconductors. BI2212. Bismuth, strontium, calcium, copper oxide is a type of cuprate superconductor. Cuprate superconductors are a family of high-temperature superconducting materials made of copper oxides. So it seems like the copper isn't necessarily an original idea. You know, it sounds like there's nothing like super original about this. It seems like people have been using copper and lead and this same kind of stuff for creating superconducting materials for a while now. So it kind of seems like really it comes down to how they're manufacturing this, right? And the only thing we know is that they're using thermal vapor deposition, this process here. But that doesn't tell us much, and I think that's probably by design, right? It's like they're not... The secret sauce is how the fuck did they make this material, and they're not going to tell you the secret sauce. The authors are getting the Nobel Prize. The first paper was 6 authors, and then they published again with 4 authors, so they are really looking for one. Damn, dude, imagine being one of the 2 authors that they that get cut from the paper. It's probably brutal. Josephson installed a thin insulator between superconductors and discovered tunneling through which current flows. Yeah, so it's these tunnels. Is kind of what I'm learning, is that the entire material isn't superconducting. It's the material has these specific tunnels, these superconducting quantum wells, and it is inside those superconducting quantum wells where you have superconductivity. And the electrons, I guess, just naturally find that path through the material. Here, I think what they're talking about tunneling, they're talking about quantum tunneling, and this is like a kind of a weird property, is that, let's see if we can find a cool picture for quantum tunneling. Yeah, this is, here, let me go, images. Yeah. So, because in the quantum world, nothing exists entirely, this is actually what I want. Open image, new tab. In the quantum world, or in the classical world, everything is a little ball, and if you throw a ball against a wall, it'll bounce off the wall. In the quantum world, everything is a probability function or a wave equation, and it's existing in all these places at the same time. So sometimes when you throw something at a wall, there's a very small probability that it'll now actually be on this side of the wall. And if you do that millions of times, sometimes it'll go through the wall. So here they're talking about tunneling, and the tunneling is occurring between these superconducting quantum wells. So sometimes an electron that is traveling through one of these superconducting quantum wells tunnels into a different superconducting quantum well, right? And if the superconducting quantum wells, they look like this. This is the side view, and then here's the top view. So there's little electrons that are traveling in these tunnels, these superconducting quantum wells, but sometimes they'll tunnel to a different one, which is kind of cool. According to Kim's paper, they used a 1250K Debye temperature for his calculation, which is mentioned for hydride. In this case, he argued that the electron-electron interaction contributes to the higher temperature superconductivity than the electron-phonon interaction. LK99 system, the applied current seems to be transported through the correlated SQW of the cylindrical column via the tunneling process and coherently transported in 3-dimension with all SQW together. Oh shit. So the electron isn't even going through a single SQW. It's going through multiple SQWs coherently. That's weird. That's some quantum weirdness right there. What does this apply for common people? So we answered that earlier, but basically magnetic levitation, very good batteries, infinitely good batteries, MRI machines in your pocket, and then quantum computing. And as soon as you have quantum computing, that's going to everything. You can now have very good simulations of physical reality, which means very good medicine. And then also AI is just going to become way crazier because we're going to be able to train way bigger models way faster. Can I talk about figure 1D? Let me see. Is this figure 1? This is figure 3. What is figure 1? Figure 1D. Temperature 10 OEs. I think each of these dots, it looks like a capital letter I. What that means is that there's an uncertainty. So there's some uncertainty to this measurement. That's what they're showing you with those little dots. And here you have DC magnetization. This is the magnetization under DC current, I'm pretty sure. EMUG. I don't know what that is. That's the unit. And field cooling versus zero field cooling. I'm not 100% sure. My guess is that field cooling refers to they're applying external cooling to this material, and then zero field cooling means they're applying no external current or no external cooling to this material. My cat is interested. Okay. So, I don't know. I can't really explain Figure 1D, unfortunately, for you. Experimental results and discussion on LK99 will be published immediately in the next paper. Yeah, these guys are on a timer now. You know, they're going to try to push ahead, but I assume there's going to be so many other research groups that are going to be pushing ahead that I don't know if these guys are going to be the next paper. You know, I'm sure other groups will come up with an even cooler version of this, including an interesting controllable levitation phenomenon and the coexistence of magnetism and superconductivity. What? Dude. Interesting controllable levitation phenomenon. That's could be pretty cool. Are we going to see a floating car? LK99 will be an attractive substance for many researchers that can solve various confusing puzzles such as the pairing process and the coexistence with magnetism. Why does LK99 exhibit superconductivity at room temperature and ambient pressure? This is because the stress generated by the Cu2 plus replacement of Pb2 ion was not relieved due to the structural uniqueness of LK99 and at the same time was appropriately transferred to the interface of the cylindrical column. In other words, the Pb1 atom in the cylindrical column occupy a structurally limited space. These atoms are entirely affected by the stress and strain generated by the Cu2 plus. Therefore, you get these superconducting quantum energy wells that can be generated in the interface by appropriate amount of distortion. The stress due to volume contraction by temperature and pressure is relieved and disappeared in CuO and Fe-based superconductor systems because the relaxation process cannot be limited due to the structural freedom. So I guess that it's all based around the fact that these lead structures inside this lattice are basically, they're already so jam-packed that once you put this Cu in there, it just kind of fucks with it even more, and you get these superconducting quantum energy wells. But if you try to do this in more traditional copper oxide or ferrous-based superconductors, which seems to be like a whole family of superconducting materials, these copper oxides, CuOs. Here's different, actually this is kind of a really cool graph. This is the year and then all the different superconductors that people have come up with. So you can see how there was a whole thread of research around these copper oxides. You see, but actually look at this. Originally, the very first thing here is Pb. So one of the very first things that people tried for superconductors in the 1900s was lead. So it seems like we went all the way back around. We went deep into all these weird elements here. Pu, Mg, Sr, Fe, Se, like all these really complicated elements. And then it seems like we're going all the way back to the beginning, back to lead. And now in 2023, basically the critical temperature of somewhere up here, you would see a little dot that says PuCu or PbCu. So kind of interesting that we went back to the beginning here. Very useful material for the study of superconductivity puzzles at room temperature. All evidence and explanation lead that K99 is the first room temperature and ambient pressure superconductor. Many possibilities on various applications such as magnet, motor, cable, levitation train, power cable, qubit for quantum computer. Terahertz antennas. We believe that our new development will be a brand new historical event that opens a new era for humankind. Dude, we did it. Holy shit. Humankind will never be the same after this superconducting material. All right, we got a bunch of references here, and then acknowledgments. Thank Professor Emeritus Vitribo. Financial support. Who the fuck are these guys? Byung Q Lee. Byung Q Lee. South Korean retired baseball player. What the fuck? And then Sewong Ki. Sewong Ki. Is that right? Oh no, one E and then one I. Sewong Ku, Chawong Ki. Chawong Ki? This guy? Sewong Kim? Wong Ki? Fuck, I don't know how like the first, last name, family name goes, so I don't know if some of these are, but they're supporting financially. Supported by the Quantum Energy Research Center, also supported by Basic Science Research Program through the National Research Foundation of Korea, founded by the Ministry of Education. So this is basically government grants. It's government money. It's not private money. Generally, that's a good thing. Generally, if it's government money, that means that it's harder to patent, which is good. If it's private research, then you bet your ass they're going to put patents all over that. But whenever it's funded through these kind of like national Ministry of Education type of grants, generally it means it's a little bit more open. So that's, I guess, a good thing. This is the guy who was responsible for LK9 synthesis, Ji-Hoon Kim. Let's look him up on Google Scholar. Google Scholar. Ji-Hoon Kim. Ji-Hoon Kim. Ji-Hoon Kim? This guy? Imaging-based thyroid, cervical. This is like a medical guy, so it's probably not this guy. What about this guy? Adaptive mesh refinement, astrophysics, dwarf galaxies. This is like a astrophysics guy, so it's probably not this guy. Dude, it's hard to find these people. I don't know if it's just because like these Korean names are a little bit, there's like more people with the same name, but I'm having a hard time finding these people. Damn, I missed a bunch of your chat. Sorry, guys. One electron with different energy. Start soon. Okay, yeah, we saw that. The authors are Nobel Prizes. Did you see the reproduction steps in the supplementary? Seems really simple to reproduce. I did not. Pretty cool. All right, let's see it. Sample synthesis and preparation. The general solid-state reaction was used. Lanarkite and CuP were uniformly mixed with a molar ratio of 1:1 in an agate mortar with a pestle. Wait, you're telling me they literally fucking like mortar and pestled? Agate, mortar, and pestle? You're telling me some dude like fucking like mixed it with his hands? Damn, dude. Okay. What about this lanarkite? How hard is that? Lanarkite. Lanarkite mineral. Lanarkite is a form of lead sulfate originally found in lead hills. It's light or green. If we try to buy this, how cheap is this? Shopping. So you can buy lanarkite. It's about $42. These seem like collector items. Lanarkite bulk supply. Lanarkite. Optical properties. It's greenish gray, white, yellow. Can I like buy pounds of this? It's not radioactive. Okay, so it seems like these are relatively cheap things. The sample is put into a reaction tube sealed under a vacuum and reacted at 900. You have to bake this bad boy at 925 degrees Celsius for 10 hours. So that seems kind of intense. I don't think you can bake this at home. After the reaction, the dark gray ingot was obtained reproducibly and then made into the shape of thin cuboids for electrical measurements. It was pulverized and used as a form of powder. Yeah, I mean, this seems pretty... There's nothing crazy here. You're just basically taking this lead sulfate looking thing and then copper, grinding it together in a mortar and pestle, and then baking it in a vacuum for 10 hours. So basically, you're slow cooking this like a bunch of ribs. Copper phosphide. That's probably super common as well. It's a dark gray ingot. You're using fucking LabVIEW. Electron paramagnetic resonance spectroscopy. I mean, these are kind of obviously much more expensive devices, but you don't actually need these, right? These are just devices that you would need to confirm that it's a superconductor. But if you just wanted to bake this at home, you could probably... I don't know if you can make this at home, but you could get close. Chemical structure of PB1 and PB2. So these are the different PB1s and PB2, which we saw in the thing, and it basically just seems like it's a different number of oxygens. Hope people are already trying to replicate the results. Yeah, that's another important thing to realize, guys, is that you can publish anything, right? Like, this could just be a bunch of lies. So until someone actually replicates this, which is kind of the whole point of science, is that you publish a paper so that somebody else can copy what you did and then replicate what you're doing. So until someone replicates this, we don't know if it's just lies or not. Is there any suspicion that the results are fabricated, or is this a real deal? I suspect it's probably real. You know, like, I don't know, like, if it was all lies, it would be a scandal, for sure. You still need a laboratory-grade furnace to cook quartz tube at a precise temperature. Yeah, how about home furnace? All right, so here we go. Here's a $1,000, or not home furnace. I want like a home metal furnace. Yeah, like one of these random like DIY propane furnaces. Like, how hot can these get? Look at this. 2,462 degrees Fahrenheit. 2 Celsius. That is more than enough. Look at that. So you can buy a $100 furnace that gets up to 1,350 degrees Celsius, and you don't even need that much. All you need for this is 925 degrees Celsius for 10 hours. And you can buy all of these. CuP3. Can you buy copper phosphide on the internet? Copper phosphide. Shopping. Zinc copper phosphide, copper 2 phosphate, Santa Cruz Biotechnology. By $20 here. You can make this at home, dude. You can literally fucking make this at home. $100, $20, and then a mortar pestle. Yeah, dude, how about that? Incoming Hupo makes superconductor at home stream. The pressure is something a basic vacuum pump can achieve. I mean, dude, this is beautiful, you know? Like, I love that AGI turned out to be super easy. You know, it's just a bunch of matrix multiplies. And that superconductivity turns out to just be baking a bunch of rocks at your house. So this is the best possible future. You know, all the technology is available. Because, you know what I'm saying? It could have turned out that a superconductor would have been like this weird fucking like rare earth element that you have to basically get in from like some child slave mine in Africa. and only the super wealthy could get it, and that would have sucked. But it seems like we got lucky, and superconductive material is basically some basic stuff, and you just bake it. So I don't know, I think we got super lucky. All right, I gotta go look at this aliens. The alien stream is gonna start at 10, so definitely check that out. But I'm gonna go do that. So let's do a quick summary, and then we'll end the stream here. So today we read First Room Temperature Ambient Pressure Superconductor. This is a paper that came out of a Korean university here, Korea University. This is all work that's funded by national and educational grants. So hopefully we can see this being continued to be open, and they don't kind of make this secret. But the TLDR is that they created a room temperature superconductor that's also ambient pressure, so it superconducts kind of sitting out in the open. And the way that they do it is by replacing one of the lead ions in this crystalline structure with a copper ion, right? And this crystalline structure of this lead apatite has a specific kind of property that it's kind of like jam-packed, and by putting the little copper in there, you pack it even more, and you get this distortion, and that distortion, or volume shrinkage, leads to a superconducting quantum well. And that superconducting quantum well has basically zero resistance. So electrons can travel through that superconducting quantum well freely. And not only that, but they actually apparently also tunnel between the different wells. So the metal is going to have a bunch of these superconducting quantum wells, which are aligned with the z-axis of this crystal structure. And yeah, that's it. That's basically it. Obviously, I don't know jack shit about chemistry and material science, so 90% of this paper I did not understand. But I'm pretty glad that we have this, and I can't wait to see all the cool applications that are going to come out of this. We're going to get super cool batteries. We're going to get MRIs that you can have at home. We're going to get levitating cars, levitating trains, and more important than that, we're going to get quantum computers, which is going to be awesome. You're going to have a quantum computer in a cell phone. So that's that. Thank you, everyone, for all the comments. There's a lot of people that commented, so I'm not going to be able to go through everyone here, but this was an awesome stream. Threw it together last minute. Did not expect this many people to come, so yeah, thanks for joining, and go out there and do something cool today. All right, see you guys later. Peace.